Hello, sir. So I'll be walking you through a telco customer churn prediction model that I created. So first, I started by importing the data and transforming it. So some columns were removed because there were empty 10-year cells, and also some values like no phone service were replaced with no, and no internet service as well. And then this data was transformed. So yeah, I some columns were continuous. They were turned into categorical. So for tenure, for example, classes were introduced based on quartiles. So yeah, basically it was turned into four different classes: new customers, short term, medium term, and long term. The same thing was also done for monthly charges, for different classes. So this was also done. Then in this new worksheet, I basically removed the customer ID column because it was unnecessary, and also insert a new column for dummy encoding, and I dummy encoded a male female. Male was chosen, so the male class was kept and the female class was basically chosen as the reference class. So if male, then 1, using different formula, of course, and if not, then 0. This was done for pretty much all the columns, including churn. And basically k-1, that rule was applied here. So 4 different classes, 3 dummy variables. Then in this sheet, the data was randomized to reduce chance of any error. And so there was a condition that we were taking to divide the data into test and training. So yeah, I decided to take 1600 ones and therefore 1600 no's for the training data set, ensuring a 50-50 split. This 1600 was taken because it was not really exactly arbitrarily chosen, but it was less than the total number of ones, but pretty high number nonetheless. And yeah, so the ones were selected after being randomized from the main data set. All right, filters were also used to get all the ones from sheet 6 into the ones sheet and paste them. And here, basically, the first 1600 ones were taken after being randomized into the training sheet. And then the same was done for zeros as well. The 1600 zeros were taken into the training data set. So now there were 3200 values. And yeah, for the test data set, we do something else. We need to figure out how much data, how many ones and zeros to take into the test data set. So the original number of the percentage in the original data set of ones to the number of the total, it was calculated, which is 26.58%. And as 3200 was our 80%, we took 80% for the training, 80-20 split, right? So 32% was 3200, 80% was 3200, so 4000 was 100%. And so basically, and so 20% of 4000 is 800. So there 800 data was required for the test set. So what is the required number of ones in the test set? This is found by multiplying the required number of total data in the test set by the percentage, the ratio of ones to total data in the original. So ones is 213 and zeros is found as well, 500 something. So yeah, 200 the cells are selected from the leftover zeros and the leftover ones, and then they are pasted into the test set. And although not quite necessary, the training set was randomized again, and the data set was, the logistic model sheet was opened with the training data set, and the model coefficients were basically set to 1. yeah, for all of the all of the variables, the model coefficients were set to 1, and the linear combination sigmoid transform and the log likelihood had to be found out. So yeah, so now these will be found out, and yeah, so they were set to 1, and sum of log likelihood needs to be maximized. First, the linear combination is found, which is found by multiplying the training data, all of the first row, except churn, with the model coefficients, which are 1 in this case, but they will change as solver is used. So yeah, it is found out, and then sigmoid transform is done on the right formula is used, and this is done to basically turn the linear output into a probability between 0 and 1, which is important for the logistic regression model. It's essential. So yeah, the formula is basically e to the power x divided by 1 plus e to the power x, and x is the value that the output of the previous step that we just did, the linear combination. So yeah, and the log likelihood is also found, which is some of this needs to be maximized. Negative values will come for each of the rows, so yeah, the sum needs to be maximized. Yeah, so initially a large sum will appear, but using solver we optimize this. So here it's showing that I add the constraints, I think -10 to 10, but then I later change this to -1 to 1 because the model some of the data had to be changed. I had to redo a part of it. I will explain that later. So yeah, solver gives a pretty good solution. Then we get the model coefficients, the right ones for the model. The ones are all changed, and then when we go to the test sheet, where we do a sum product of the row in the test sheet, and here you will notice that there is no column of ones. That was the intercept column that was in the logistic regression model. And yeah, so this is multiplied with model coefficients save for the intercept, and then the intercept is added, and these values are locked to ensure that the wrong values are not used. And then the probability is estimated using the exponential, the sigmoid transform formula. Basically, this is the probability for each of the customers. So the performance of this model is now analyzed. So the minimum predicted probability, the minimum probability is taken from the test set. The minimum and the maximum predictions, they're both taken, and the first cell is set as 0.01 and the step value is set as 0.05, and the false, okay, the stop value, sorry, is set at the maximum prediction. And yeah, it's to find the false positives, the false positive rate at that probability cutoff. We'll use the let function, and we're basically finding the false positive count divided by the all negative count, which gives the false positive rate. And for the true positive rate, we do something similar, where we also use the let function, but in this case, the formula is the true positive count divided by all positive count, right? And yeah, this gives us the true positive rate for that cutoff, and then we get it for all the other cutoffs as well. And Next step, we need to make the ROC curve. So we insert a scatter with smooth lines, and fortunately it is the area is greater than 50%, as you can see. Oh yeah, so the problem here is that so I missed the moderate monthly churn. I did not I did dummy encode it, but I did not include it for some reason. While copy pasting, it went away. So yeah, the things had to be changed. The data set was scrambled and I did it again. And so yeah, I find the area under the curve in this next step. A formula is used for this. So like the trapezoid formula, area under a trapezoid. So yeah, we do eventually get the area under the curve. Like we have to sum the entire column to get the total area under the curve. And yeah, it's greater than 50%, as you can see. So the model has predictive value. Yeah, so now we choose the cutoff. The cutoff I decided to select was 0.4 or 0.396 something, and I selected this for a few reasons. So the cost of churn to a telco is pretty damn high because lifetime value of customers is high. So I chose a relatively low cutoff. Even if there are false positives, it's not that big of a problem compared to false negatives. The actual probability is whether the customers actually churn or not. The predicted probability is the if the actual the table probability is the test set probability is greater than the cutoff that we selected, then it's 1. If it's not, then it's 0. The cutoff is 0.4. So we count the true negatives first. It's a true negative if predicted probability is 0 and actual probability is 0. And we do it accordingly for the false positives, which is when predicted probability is 1 but actual probability is 0. And also for the and so yeah we also do this for false positives as well, as I said. So here you will see that our false positives is kind of high, but it's so precision may be lower, but we need to according to the logic, the true negative is also high, and we need to make sure that customers do not churn. That is our main goal. So even sending a text message to them, an email, won't cost much, but losing out on the lifetime value is very costly. So yeah, we find the accuracy. True negatives and true positives divided by the total, and precision is the true positive divided by the false positives plus it's plus the true positives itself. So precision 45.68%, accuracy 69%. We call true positives divided by false positives plus true positives. This is pretty high, and we need to keep this high. Specificity is found as well as the F1 score. The F1 score is basically 2 times these are model validation metrics. Yeah, so the formula is there, and the area under the curve is the sum of all of the areas that we found before. So it's 83.21, much greater than 50%. Next, let's interpret the coefficients. They're arranged in descending order. So fiber optic internet users are the highest. It has the highest positive coefficient, so that means that they're most likely to churn. And the intercept is basically the reference class, how likely they are to churn, so 0.37. And when it's negative, for example, for those customers with long tenure or long contracts, it's negative, so that means that they're less likely to churn. The in-depth explanations are in the report. That's me, Ayman Zaman, signing off.